All right. Problem solving with quadratics. So, I mean, we didn't write everything out, but this is the gist of what the problem is. They've given us a diagram, and they've told us that there's 1, 2, 3, 4, 5, 6, 7 vertical pieces of fencing that are connected by two long ends. Okay, we will call these the widths. width. I don't know why that looked funny. And then these other two we'll call the lengths. Okay, so we'll put like an L there. So there's two L's, and then there are, if we write a W for each, there are 7 W's in this case. Okay? They've told us there's 7 lines. There's a total of 1,400 meters of fencing, and we got to maximize area in between each of them. Okay, now this isn't to scale. Obviously, this area is significantly bigger than this one. We just don't know where to put them. Our goal is to maximize the area of this object. If it was a single rectangle, that's really easy. We just try to make it as square-like as possible, and we get it. But it's not. We got all these sections in between. So, really what this is asking is about 2 different types of measurement. The one that gives a number of fencing is perimeter. Okay, so perimeter is going to be important to this. We have our perimeter, which will represent as P. And then the second piece is maximizing area. So we have area, which we'll just call A in this case. Okay, we need general formulas for these. So perimeter, technically, you got to add up every side. So side plus blah, 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 all the sides involved. Area, in this case, is going to be kind of, it's just going to be length and width. Okay, because this is actually just one large object, right? So the area is a lot easier because we're just doing length times width. Perimeter is what's difficult. We have all these extra pieces in between. But we can simplify it because a lot of the sides are like sides. So I'm going to bring down that perimeter again. And the perimeter, we can actually represent, we had W's, right? And in fact, we had 7 W's. So there are 7 widths that are part of this. And then we have lengths. Well, we have 2 lengths. So our perimeter is actually the addition of those 7 widths plus those 2 lengths, and that's the entire perimeter of the shape. Well, they've told us how much fencing we have. The total fencing is actually the final perimeter. So the perimeter of the object is 1,400, I think, meters, feet. I don't remember what this is. What units we'll call them, okay? And it's subject to these 2 variables, all right? Whatever the widths and the lengths are. Now, they can't be unlimited. I can't just say this is a million, this is a million. It won't quite work out. So what we want to do is we want to actually isolate for one of these variables. We want to set this equation equal to L or W. The reason we want to do that is because of this area. We want to maximize, hello you, we want to maximize the area of length times width. But the problem is I have 2 variables. So I'm going to use this. We'll call that equation 1. We'll call that equation 1, and we'll call this equation 2. What we're going to do is we're going to isolate equation 1 for one of the variables, and then we're going to substitute it into equation 2. And that way, we'll have an area that's only subject to one of the variables, either the L or the W. This will allow us to maximize stuff, and it's going to set up like a quadratic relationship. So, I really like the L because it has the number 2 on it. I think it'll be a nicer value to probably work with. So I'm going to move the 7 over. So I'm going to get negative 7W plus 1,400 is equal to 2L. And again, I got to isolate that single variable, so I got to divide all my terms by 2 here. So L is equal to this 1,400 divided by 2 is actually 700. This ends up being a not so lovely fraction here. Negative 7 over 2W. Okay. Well, we have this. So now what we're going to do is we're going to substitute it in for the L in the area. And that will give us an area that's only subject to width. So in other words, we're going to solve for whatever the width will have to be in this case. So when we do that, our new area formula is going to be W times, and then the rest of this. So I'm going to substitute this in 7 over 2 W plus 700. Okay? So this is the area formula. Now this is something, this specific version of it, I'm going to come back to because it's actually really handy here. But I just want to relate to what kind of relationship we have. If I decide to distribute this, okay, I'm going to get an area that is equal to negative 7 over 2W squared plus 700W. And I'm just going to put a plus 0 at the end And the reason I'm going to do that is so that we can visually see that this is actually really similar to the standard form of a quadratic. Okay, plus x and plus c. So you'll see we actually have each of these values here. Now, the problem here is we need to maximize area. And if we're talking about a quadratic relationship, which we just figured out it is, if I do a general quadratic, and we take a look at this one, we know that, oh yeah, the a value is a negative. Whoops, take that away. The a value is negative, which means this has some relationship that's opening downwards. That means this is the max. In other words, vertex. So I need to find the vertex of this. Now, in standard form, which is the time we just made, I can complete the square, use a formula, but this isn't a wonderful one. Like I have a fraction here. It might take a while completing the square this way. But if I jump backwards, technically this is very similar to a factored form. In fact, I can easily, because they're isolated, here's one factor, here's another factor, I can set them equal to 0 and find my x-intercepts. From my x-intercepts, I can then find my axis of symmetry, which will help me find the vertex. I actually think that might be faster. Okay, and I know that's kind of a roundabout route, but because the completing the square might be somewhat difficult, we're going to use this route instead. So what we're going to do is we're going to set the area equal to 0, and we get w as one of the factors, and the other factor is negative 7 over 2w plus 700. When we set it equal to 0, one of these factors has to be 0. The only way to multiply to 0 is by multiplying by the number 0. So we're going to get w is equal to 0, a width of 0, which that doesn't make sense. That definitely can't be our answer. And we get another answer of 0 is equal to negative 7 over 2w plus 700. Well, let's isolate for the w here. I'm going to move that 700 over. It becomes negative 700 is equal to negative 7 over 2w. I'm going to multiply both sides of the equation by 2. When I do that, I'm going to get negative 14,000 is equal to, when we multiply this side by 2, we'll get negative 7w. And then we just got to isolate that w, so we divide by negative 7 on both sides. And we're going to get a width that's equal to negative divided by negative is a positive, 200. So if we go back up, what we've just discovered is in order to maximize the area, we need these widths to be 200, okay? Now, we can use that information to figure out the lengths of this. We know our perimeter. Where's my perimeter formula? Here it is. My perimeter formula is here. We've just discovered that width is 200. We can plug that in, and we know that the perimeter is 1,400. That's all the fencing we have. And we can isolate for our L in this case. So I'm going to take this formula, bring it down here, 1,400. That's how much fencing we had, is equal to those 7 widths, which are each 200 units. And that will help us isolate for L. We can figure out what our L is in this case. Okay. Oh, I'm so sorry. That's not what I was doing. Oh, I'm glad I did this. I'm going to follow this through. This ends up being 14,000 plus 2L. I spoke a little too soon. I bring that over, I get 0 is equal to L, L equals 0. That doesn't make sense. The reason being is I forgot what I was actually doing. I found the two x points. One of them happened to be at 0, and the other happened to be at, what did I just say the other one was? Down here, 200. There we go. Sorry, I'm glad we did that. I was able to see my error. These are the two x values, so if I were to update this a little, there we go. 0 and 200 are the x-intercepts. The middle of those two would be the vertex. Any idea what the middle of 0 and 200 is? That's it. So that means the x value of the vertex, okay, is 100. In other words, our widths should actually be 100. So now I can use that information. The 1400, that perimeter formula, those 7 widths are 100 each, plus the 2 L's, okay? That's going to be 700 is equal to 1400 plus 2L. When I subtract or bring over the 700, I'll get 700, that should be an L, is equal to 2L. And when I divide both sides by 2, I'm going to get L is equal to 350. So what we just did, I'm glad I kind of messed it up. It gave me a little more clarity of what we were doing here. What we just discovered is that this length here should be 350. This length should be 350. And each of these widths should be 100. Okay? And if you remember, there's technically 7 of them. It kind of splits 1, 2, 3, 4, 5. There we go. So is that right? 1, 2, 3, 4, 5, 6, 7. Yeah. We have 7 lines across. This is the makeup of our maximum area with a specific perimeter and all these special widths in between. Okay? So, just to do a quick recap, because that is a tricky question. We take that original perimeter and we set it equal to one of the variables. We then plug that into the area formula. So that area is subject to just a single variable, width or length. We could have isolated for the other one. Once we did that, we set it equal to 0 to find the x-intercepts, which is where I made a mistake. I thought it was almost done before I was. And we got our 2 x-intercepts, which we put up here. Okay. I thought I was done, but when I plugged it in, I got a 0, which reminded me, no, you didn't find a maximum, you found zeros. Once I have those 2 zeros, I find the middle of them, or the average, and that gives me the maximum width value. Using that width value, which is 100, I plug it back into the perimeter formula, and that helps me find the other lengths in this formula. Okay? A lot of steps to this question. Very, very complex, I guess we could say.